You're driving down a quiet, tree-lined street. The radio is playing, the windows are down. You're just cruising.
Sounds nice.
Yeah, right. And then out of nowhere, a squirrel darts right into the middle of the road.
Oh, no.
Yeah, and in that split second, your conscious brain doesn't even have time to form a sentence. You don't think about it. Your foot just, bam, slams on the pedal.
Right, it's pure instinct.
Exactly.
Yeah.
Your seatbelt locks, the tires chirp, and your 2-ton vehicle comes to a complete immediate stop. The squirrel freezes, looks at you, and just casually scampers up a tree.
Like nothing happened.
Like nothing happened. And you're sitting there, heart pounding, gripping the steering wheel. And we do this all the time. We trust our vehicles to stop, but we rarely take a moment to think about the incredible, like almost invisible physics that actually make that violent deceleration possible.
It really is a remarkable sequence of events that we just take for granted every single day.
Yeah.
I mean, we expect a 4,000-pound machine moving at highway speeds to just shed all of its momentum in a matter of seconds, and we completely ignore the sheer magnitude of energy that must be managed and routed and dissipated to keep us from careening into a tree.
Well, today we are exploring exactly that. We're doing a deep dive into the engineering and the physics of how we stop moving objects.
And we have some fascinating source material for this one.
We really do. We are looking at a huge stack of sources today. We've got engineering journals, some historical patents, which are super cool, commercial truck manuals, physics textbooks, and even some amusement park forensic reports.
Yeah, the amusement park stuff is wild.
It is. So we're looking at the whole spectrum of deceleration today, from the raw thermodynamics of friction to the fluid mechanics of heavy machinery, and finally into the completely mind-bending world of electromagnetic forces. So, okay, let's unpack this.
Let's do it.
Before we get into the complex fluids and magnets and all that, we have to start with the fundamental goal of all braking systems. Because from the reading, it seems like it really just comes down to energy conversion.
That is the absolute core of it, yeah. Braking is not about destroying motion.
Right.
Because, the first law of thermodynamics dictates that energy cannot be created or destroyed. It can only be transformed.
Right, you can't just delete the forward momentum.
Exactly.
Yeah.
When a vehicle is rolling, it possesses a massive amount of kinetic energy. So to arrest that forward momentum, you have to force that kinetic energy to change states. And in traditional braking systems, you are forcing kinetic energy to become thermal energy. You're basically turning speed into heat.
Turning speed into heat. I love that phrasing. So in that split second with the squirrel, my car's forward motion was quite literally being incinerated.
Basically, yes. The brake system induces controlled friction, and that friction absorbs the kinetic energy, instantly converting it into thermal energy that just radiates into the surrounding atmosphere.
Wow.
And the scales here are staggering. Because the amount of kinetic energy, it scales with the square of your velocity.
Wait, the square?
Yeah, the square. This means if you double your speed, your brakes don't just have to manage twice the energy, they have to manage 4 times the amount of energy.
Oh, wow.
Which means 4 times the amount of heat.
I didn't realize it scaled like that. Which totally explains why early automotive engineers struggled so much with thermal management, right?
Oh, absolutely. It was a huge problem.
Because if you look at the older design, the drum brake, it's essentially this heavy metal bowl attached to the wheel hub. And inside that bowl, you have these curved brake shoes that expand outward to press against the spinning inner wall. But because that reaction happens inside a closed metal drum, the heat just has nowhere to go. It just bakes inside that bowl.
Yeah, and that trapped heat is the absolute enemy of friction.
Right.
When those internal temperatures spike during heavy braking, say you're navigating a really steep mountain pass, the materials actually begin to off-gas.
Like they melt.
Not melt exactly, but the resins in the brake shoes vaporize. And that creates this microscopic cushion of gas between the shoe and the drum. So the brake shoe physically cannot touch the metal anymore.
Because the gas is in the way.
Exactly. This is what we call brake fade. You press the pedal, but the stopping power just vanishes.
That sounds like a complete nightmare. Just stepping on the pedal and nothing happens on a mountain pass.
It was terrifying.
Which I imagine is what drove the industry's shift toward disc brakes.
Very much so.
Because with a disc brake, you have a heavy flat metal rotor spinning out in the open air rather than enclosed in a bowl. and a caliper that acts like a vise, right? Pinching the rotor with two brake pads.
Yeah.
And because it's fully exposed to the turbulent air rushing under the car, it sheds that thermal energy much more efficiently.
Right, the airflow is constantly cooling it.
But what really fascinated me in the sources is the material science of the pads themselves, specifically ceramic brake pads.
Huh?
Because when I hear ceramic, I think of like a coffee mug, but they aren't just made of kiln-fired pottery.
No, they were highly engineered composites.
Right. They use clay and porcelain, but then they interweave copper filaments throughout the pad. Why copper?
Well, the copper serves a dual purpose. First, copper is highly thermally conductive, so it acts like a heat sink, drawing the thermal energy away from the friction surface and dispersing it through the backing plate, so it cools the pad down faster.
Okay, that makes sense.
But the second benefit of that specific composite, the clay, porcelain, and copper matrix, is actually acoustic.
Yeah, this is the part that totally blew my mind.
Wow.
Because the combination of those specific densities alters the resonant frequency of the brake pad.
Exactly.
When the pad clamps down on the spinning steel rotor, it vibrates, just like a bow being drawn across a violin string. But the unique mass and stiffness of the ceramic copper composite forces that vibration to happen at an incredibly fast rate.
Much faster than standard organic pads.
Right, it pushes the wavelength of the sound so high that the acoustic frequency enters the ultrasonic range. So at physically squealing, it's screaming, but the pitch is beyond the anatomical limits of the human eardrum.
It is such an elegant solution. I mean, you are engineering the material not just to survive a high temperature phase change, but to actively manipulate the acoustic output for human comfort. You are hiding the violent reality of the friction in a frequency we simply cannot perceive.
Which is brilliant. It makes you feel like you have this quiet, luxurious ride when really there's a banshee screaming at your wheels.
Exactly.
But okay, if the goal is just clamping a pad onto a rotor to create friction, I have a fundamental question about the architecture of the car itself. Like, why do we need this elaborate network of fluid-filled pipes running all through the chassis?
You're talking about the hydraulic lines.
Right, because if I pull the brake lever on my bicycle, it's just a braided steel cable that physically pulls the brake pads against the rim. It's direct, it's instantaneous, so why can't a car just use a heavy-duty mechanical cable connecting the brake pedal directly to the calipers?
It's a great question. And to understand why that fails, we have to look back at the early days of automotive design, like in the 1910s and 1920s.
Okay.
Early cars actually did rely on mechanical linkages. It was this complex web of steel rods and levers and cables underneath the car. But a cable is a physical object subject to the laws of metallurgy.
Yeah.
Over time, under the immense strain of stopping a vehicle, steel cables stretch. Linkages bend and they wear down.
And I imagine they don't wear down with perfect symmetry.
That is the fatal flaw right there. Imagine you're driving a heavy car from that era at highway speeds. You press the brake pedal, which pulls a lever, which then pulls two cables, one to the front left wheel, one to the front right.
Okay.
But let's say the cable routed to the left wheel has stretched just 2 millimeters more than the right over the past year.
Oh, man.
Yeah. When you apply pressure, the right wheel locks up hard, while the left wheel barely receives any clamping force at all.
So you have a massive deceleration force on one side of the vehicle and almost none on the other. That torque would just violently rip the steering wheel out of your hands and throw the car into a spin?
It was incredibly dangerous.
Yeah.
Automotive engineers quickly realized that to stop a heavy, fast-moving object safely, the force applied to all four wheels must be perfectly instantaneously equal. And that has to hold true regardless of the vehicle's age or how much it's been worn down.
Right.
Mechanical linkages simply cannot guarantee symmetrical force distribution.
Which brings us to the engineer Malcolm Lockhead,
Yes.
who, fun fact, eventually founded the Lockheed Aerospace Company. He just changed the spelling of his name.
Right, yeah.
In the late 1910s, he revolutionized automotive safety by abandoning wires and turning to fluid mechanics. And he applied a principle discovered way back in the 1600s by the French mathematician Blaise Pascal.
Pascal law. It is the absolute bedrock of modern hydraulics. It basically states that when pressure is applied to a contained, incompressible fluid, that pressure is transmitted equally and undiminished in every possible direction throughout the fluid.
I try to visualize this like pushing down on a fully inflated air mattress in a swimming pool.
Okay, I like that.
If you press your hand into the center of the mattress, the pressure doesn't just stay under your hand. The displacement forces the corners of the mattress to bulge outward instantly. The The pressure distributes across the entire volume of the thing.
That's a great analogy. And Lockheed essentially did this with steel pipes. He connected all four wheels to a single central reservoir of fluid. When you press the brake pedal, a piston pushes into that fluid. And because the fluid can't be compressed, that pressure wave travels through the pipes and hits all four wheels at the exact same microsecond with the exact same amount of force.
No pulling, no uneven stretching.
Exactly. But the fluid is doing something far more vital than just ensuring symmetrical timing. It is actively multiplying your physical strength.
Because my leg is not strong enough to stop a car.
No, definitely not. The force required to stop a moving vehicle is vastly greater than the strength of a human leg pressing a pedal. So, hydraulics solve this through the geometric relationship between two cylinders. The master cylinder at your foot and the slave cylinders down at the wheels.
Okay, let's put some numbers to this multiplication because this is where the math feels like magic. If the master cylinder attached to my brake pedal has a very narrow diameter, but the slave cylinder pushing the brake pads at the wheel has a surface area that is, let's say, 4 times larger, what happens to the force?
Well, because the fluid is incompressible, the pressure acts on every single square inch of the surface it touches. So if you push the small master cylinder with 10 pounds of force, that pressure travels through the fluid and spreads across the much larger surface area of the slave cylinder. Because the wheel cylinder is 4 times larger, it multiplies your 10 pounds of input into 40 pounds of clamping force at the rotor.
That is wild. It just scales up.
It does. But, the laws of physics demand a trade-off. You don't just generate free energy out of nowhere.
Right, there's always a catch. What's the trade-off?
The trade-off is distance. To move that larger cylinder at the wheel, you have to displace a large volume of fluid. Because your master cylinder is narrow, you have to push its piston much further down the tube to move enough fluid.
I see.
So your foot might have to push the brake pedal down 40 millimeters just to make the brake pads move 10 millimeters at the wheel. You are trading a long, easy push at the pedal for a short, immensely powerful squeeze at the rotor.
It's just an elegant leverage system.
Exactly.
But it entirely relies on the chemical integrity of the fluid inside those lines. Because we use highly engineered synthetic fluids like DOT4, which is a polyglycol ether mixture, and from the source material, it's designed this way for one very critical reason: resistance to phase changes.
Yes.
Because we established earlier that braking generates astronomical amounts of thermal energy. That heat transfers from the rotor into the brake pads, through the caliper, and it goes directly into the hydraulic fluid.
And that thermal transfer represents the most dangerous vulnerability in a hydraulic system.
Yeah.
The fundamental requirement of hydraulics, like we said, is that the medium must be incompressible.
Right.
Liquids are incompressible. Gases are highly compressible.
So if the brake fluid gets so hot that it exceeds its boiling point, it undergoes a phase change. The liquid vaporizes into gas bubbles inside the steel brake lines.
This is known as vapor lock.
Yep.
And it's incredibly dangerous. Standard DOT4 brake fluid is engineered to have a dry boiling point over 440 degrees Fahrenheit to prevent this exact scenario. Because if the fluid boils and introduces gas into that closed system, the next time you press the brake pedal, the master cylinder piston pushes forward, but instead of that force traveling to the wheel,
It just compresses the gas bubbles.
exactly, it simply compresses the gas bubble.
So the pedal just feels mushy or spongy, and it sinks right to the floorboard, and the car doesn't slow down at all because the kinetic energy of your foot is just squeezing vapor instead of moving the heavy brake pads.
It results in a total catastrophic failure of the braking system. And this is also why brake fluid is hygroscopic, meaning it absorbs moisture from the air over time.
Which seems like a bad trait for something that shouldn't boil.
It is, but it's unavoidable with those chemicals. As it absorbs water, which obviously boils at a mere 212 degrees, the overall boiling point of your brake fluid steadily drops, which makes vapor lock much more likely under heavy braking if you don't change your fluid regularly.
Man, that vulnerability leads to another really obvious question. What happens if, a rock kicks up on the highway and severs the rubber hydraulic line running to my front wheel? If the fluid leaks out, there's no pressure and I lose my brakes, right?
Well, automotive engineers mitigate that risk through a dual circuit system. Inside modern master cylinders, there are actually 2 separate pistons working in tandem, and they feed 2 completely isolated networks of brake lines, Commonly, this is arranged in a diagonal split.
Okay, a diagonal split.
Yeah, so one independent circuit controls the front left and rear right wheels, while the other completely separate circuit controls the front right and rear left.
Oh, that's smart. So a severed line only drains half the system. The other closed loop maintains its hydraulic pressure, meaning you still have half your stopping power.
Exactly. It's a brilliant built-in failsafe.
It is, but I have to challenge this whole fluid dynamic paradigm when we scale up to commercial transportation.
Okay, let's hear it.
If we look at an 80,000-pound big rig hauling freight down the highway, they don't use hydraulic fluid, they use air brakes.
They do.
But wait, you just spent the last 5 minutes explaining that gas is highly compressible and that air in a brake line causes fatal vapor lock. Why would a massive commercial truck rely on the exact pneumatic properties you just said are incredibly dangerous?
I know, it seems entirely counterintuitive. But it makes sense when you examine the mechanical architecture of a heavy-duty air brake. A commercial truck flips the entire safety paradigm in reverse.
How so?
Well, in your passenger car, the default state of the brake is open. The wheels spin freely. You have to actively introduce hydraulic pressure to clamp the brake shut.
Right.
In an air brake system on a heavy truck, the default resting state of the brake is completely locked shut. It is forced closed by an immensely powerful mechanical coil spring inside the brake chamber.
Oh, I see. The pressure isn't doing the braking.
Precisely the opposite. The truck has an onboard engine-driven compressor that generates massive air pressure. That compressed air is routed into the brake chamber, specifically to push back against that heavy spring, pulling the brake pads away from the drum.
Wow. So the truck requires active air pressure simply to move.
Exactly. When the truck driver steps on the brake pedal, they aren't pushing air into the brakes. They are actually venting air out of the system.
They are releasing the pressure so the mechanical spring can slam shut.
Yes. That completely changes the failsafe dynamics. If an airline is severed on an 80,000-pound truck, or the compressor fails entirely, the air just rushes out. And without that pneumatic pressure holding the spring back, the spring violently expands and locks the wheels.
That is amazing. It is a true fundamental fail-safe mechanism. A catastrophic loss of system integrity results in the safest possible state. A sudden, abrupt halt.
Right. The truck physically cannot roll without a functioning pressurized system.
That solves the fail-safe issue beautifully. But even with these brilliant hydraulic and pneumatic architectures, we are still relying on a pretty primitive concept at the very end of the line, which is physical friction.
Sure.
We are still just pressing two materials together until the kinetic energy burns off as heat. And where there is friction, there is degradation. Rotors warp, pads turn into toxic dust, components require constant maintenance. Which brings us to the largest leap in our exploration today.
Yes, the big one.
What if we could stop a high-speed vehicle without physical contact? What if we could manipulate invisible forces to arrest kinetic energy?
Now we cross the threshold into the realm of electromagnetism.
Yes.
And, the desire to use electricity for braking is not new. In 1887, a brilliant electrical engineer named Granville Woods actually patented an electromagnetic brake for the railway industry.
But Wood's design was essentially a hybrid, right? From what I read, he was using electricity as the muscle, but it was still technically a friction brake.
That is correct. Instead of relying on a human pulling a lever or a pneumatic compressor, Woods routed an electric current through a copper coil to generate a magnetic field. That magnetic field was strong enough to physically pull a heavy iron armature against the wheel, creating friction.
Okay, so it was a massive leap forward in actuation speed and reliability, but it still relied on physical contact to generate thermal energy.
Exactly. It was still rubbing metal on metal.
Okay, here's where it gets really interesting. Because we can evolve past Wood's design,
Right.
we can eliminate the friction entirely, we can brake using nothing but the subatomic resistance of the universe.
I like how you phrase that.
It sounds like sci-fi, but this is the eddy current brake.
The eddy current brake is, without a doubt, one of the most elegant applications of physics in modern engineering. It relies on two foundational principles of electromagnetism: Faraday's law of induction and Lenz's law.
Okay, let's break down the mechanics of this without getting bogged down in the textbook math. If I have a piece of conductive metal, let's say a heavy aluminum fin, and I pass a strong magnetic field over it, what is Faraday's law actually doing inside that metal?
So Faraday discovered that a changing magnetic environment forces electrons to move. When your aluminum fin passes through the magnetic field, the shifting magnetic flux lines sweep through the atomic structure of the metal. This disturbance induces an electromotive force, which creates localized circular currents of electricity swirling within the aluminum itself.
Like little electrical whirlpools.
Yes, exactly. These microscopic tornadoes of electricity are called eddy currents.
Okay, so the motion through the magnetic field generates these swirling electrical currents inside the metal fin. But how does that actually slow the vehicle down? Why doesn't the fin just keep moving while carrying those new electrical currents?
This is the genius of Lenz's law. Lenz mathematically proved that nature abhors a change in magnetic flux. When those swirling eddy currents are born inside the aluminum, they act like tiny electromagnets. They instantly generate a magnetic field of their own.
Oh, wow.
And crucially, Lenz's law dictates that this newly induced magnetic field will always perfectly oppose the original magnetic field that created it.
It creates its own counterforce.
Yes.
I think of this like wading into a swimming pool. If you walk slowly through waist-deep water, the resistance is minimal, right? You just push right through. But if you try to sprint through that same water, the fluid dynamics push back violently against your shins. The harder and faster you push against the water, the more exponentially the water resists your motion. The magnetic field is the water.
That is an excellent way to visualize it. The faster the aluminum fin moves through the primary magnetic field, the stronger the induced eddy currents become. Stronger eddy currents generate a vastly stronger opposing magnetic field. The system is inherently self-regulating. The resistance scales non-linearly with velocity.
This scaling factor is why eddy current braking is the gold standard for high-speed rail, right? Like the Japanese Shinkansen bullet trains.
Oh, absolutely.
Because when a train is hurtling down a track at 200 miles per hour, applying a physical friction brake would be catastrophic. The sheer volume of kinetic energy converted into heat would warp the steel rotors and just disintegrate the brake pads in seconds.
The thermal load would easily exceed the material limits of the metals. It would just melt. But with eddy current brakes, the Shinkansen simply lowers an electromagnet near the steel rail. At 200 miles per hour, the relative motion between the magnet and the rail is extreme. This induces a massive eddy current within the rail, generating an opposing magnetic field so powerful that it decelerates hundreds of tons of train without a single component ever touching the rail.
That is incredible.
There is no physical contact, no mechanical wear, and no friction dust. It's perfectly smooth.
But there is a glaring limitation to this invisible force inherent in the physics we just described. Because the opposing force is generated by the change in the magnetic flux. It relies entirely on motion.
Right.
So what happens to this incredibly powerful braking force as the Shinkansen slows down to, say, 5 miles per hour?
Well, as the velocity drops, the rate of changing magnetic flux drops. The eddy currents weaken, the opposing magnetic field weakens, and the braking force just dissipates.
And when the train reaches exactly 0 miles per hour?
At absolute zero velocity, there is zero changing flux. The eddy currents cease to exist entirely. This means an eddy current brake has absolutely zero holding power when stationary.
Wait, none?
None. You could possess the most advanced electromagnetic braking system on Earth, but if you park that vehicle on a slight incline and turn off the propulsion, it will simply roll away.
Oh man, so you must always integrate a secondary traditional friction brake just to serve as a static parking brake.
Always. You can't beat that physical reality.
That is fascinating. Now, the topologies of these systems usually take two forms, right? Circular and linear.
Yes.
The circular form is a conductive disc spinning between stationary electromagnets. We see this heavily in fitness equipment, those high-end rowing machines that offer perfectly smooth, fluid resistance without any grinding parts.
Right. It feels completely seamless.
We also see it in industrial circular saws, where an eddy current brake can arrest a blade spinning at thousands of RPMs in a fraction of a second when the trigger is released.
Yeah, the linear topology is what we see in the Shinkansen, or in modern roller coasters. Instead of a spinning disc, you have a straight track of conductive fins, and the magnets are mounted to the moving vehicle, or vice versa.
Which brings us to perhaps the most extreme, high-stakes application of linear eddy current braking, the amusement park drop tower.
Oh, these are fascinating from an engineering standpoint.
I mean, think about it. You get strapped into a gondola, hoisted 300 feet into the air, and dropped into a complete free fall, reaching speeds over 70 miles per hour. The deceleration at the bottom of that tower has to be flawless every single time, thousands of times a day.
And this is exactly where engineers strip away every possible point of failure. On a drop tower, they do not use electromagnets.
Why not?
Because electromagnets require a live power grid, wiring harnesses, and computerized control systems, all of which can fail. A power surge, a severed wire, a software glitch. Any of those would be catastrophic.
Right.
Instead, the drop gondolas are equipped with arrays of rare earth permanent magnets.
Permanent magnets require zero electricity.
Zero. They just possess a permanent magnetic field by virtue of their atomic alignment.
Exactly. The track itself is lined with vertical fins of highly conductive copper or aluminum. When the gondola is dropped, it accelerates toward the Earth. As the permanent magnets on the gondola plunge over the conductive fins at the bottom of the tower, the extreme velocity induces massive eddy currents in the fins. And the resulting opposing magnetic field acts like a dense, invisible cushion, smoothly decelerating the gondola. It is the ultimate mechanical failsafe.
It truly is.
If the entire amusement park loses power in a catastrophic grid blackout while you are in freefall, you are completely safe.
Because the deceleration doesn't rely on software or electricity. It relies on the immutable laws of the universe. The falling motion guarantees the eddy currents, which guarantees the opposing field, which guarantees you will stop. The physics cannot be turned off.
However, recognizing the perfection of the physics forces us to confront the vulnerability of the system as a whole. Because a perfectly engineered electromagnetic failsafe is still embedded within a broader context of human operation and digital oversight.
That is the tragic irony of complex systems, yeah.
If the physics are guaranteed, how do these systems fail? This leads us to a forensic engineering report regarding a devastating tragedy in 2022. The death of a 14-year-old boy named Tyre Sampson on the Orlando Freefall Drop Tower. We have to look at the intersection of perfect mechanics and human error.
It is an incredibly critical case study in systems engineering. The investigation into the Orlando freefall confirmed that the eddy current brakes did not fail.
Right.
The rare earth magnets and the conductive fins performed exactly as Lanz's law dictates. The physical deceleration of the gondola was entirely nominal. The catastrophic failure occurred in the digital architecture, specifically the sensor interlocks designed to verify rider safety.
To operate safely, these rides use automated proximity sensors on every seat's over-the-shoulder harness. When you pull the harness down, the sensor measures the gap between the restraint and the seat. It feeds that data to the ride's central computer. If the sensor detects that the harness is open too far to safely secure the specific dimensions of the rider, the software interlock prevents the ride's dispatch sequence. The computer simply refuses to let the gondola lift.
It is a digital failsafe designed to prevent human operators from making a fatal judgment call regarding a rider's size. It takes the human element out of it.
But the forensic investigation revealed that the sensors on two specific seats had been manually compromised. The operational baseline allowed for a harness gap of approximately 3 inches. The sensor on the seat Tyre Sampson occupied had been manually adjusted with tools to allow an opening of nearly 7 inches.
This modification broke the chain of safety. By manipulating the sensor's physical placement, the system was tricked. The harness was resting at a 7-inch gap, but the sensor transmitted a signal to the computer indicating the restraint was in the safe, closed position. The software interlock was bypassed, and the ride was allowed to dispatch with a passenger who was too large for the mechanical constraints of the seat.
When the gondola entered the braking zone at the bottom of the tower, the eddy current brakes applied their massive, instantaneous deceleration force. The physics worked perfectly, but because the harness gap was artificially widened, the restraint could not hold his mass against the negative G-forces, and he was ejected from the seat.
It is an incredibly sobering reality.
It really is. You can harness the fundamental forces of electromagnetism. You can build a physical braking architecture that requires no power and defies failure. But if the digital interlocks are manually overridden or the human-machine interface is compromised, the physical perfection is rendered completely useless.
It highlights a paramount rule in engineering. A system is only as robust as its most vulnerable component.
Yeah.
We often focus on the heavy mechanics, the magnets, the hydraulics, the rotors. But the digital sensors and human operators overseeing those mechanics are equally critical to the physics of stopping safely.
We put so much immense trust in these unseen forces every single day, usually without a second thought. And we have covered incredible ground today. We looked at the raw thermal violence of converting kinetic energy into heat and how engineers weave copper into ceramic to hide that violence in ultrasonic frequencies. We explored Malcolm Lochhead's hydraulic revolution, utilizing Pascal's law to multiply our physical strength through incompressible polyglycol fluids. We examined the reverse-engineered safety of commercial air brakes. And we ventured into the invisible subatomic world of eddy currents, where moving metal fights against its own induced magnetic fields.
It is a profound evolution of technology. I mean, we have moved from simply pressing objects together to create friction to manipulating the fundamental fluid dynamics of liquids and gases, and finally to harnessing the quantum realities of electromagnetism to resist motion without ever making contact.
The next time you press your brake pedal to avoid a squirrel on the road, or you pull the lap bar down on a roller coaster, you don't have to just trust the system blindly. You can visualize the complex fluid dynamics routing through the steel lines under your feet. You can picture the swirling tornadoes of magnetic fields pushing back against gravity on the drop tower. It is a symphony of applied physics happening right in front of you.
Understanding the mechanics beneath the surface truly changes how you interact with the built environment. The world becomes far more intricate and fascinating when you know how the magic trick actually works.
Absolutely. So what does this all mean for the future? With the massive global shift toward electric vehicles, we are seeing the rise of regenerative braking. Instead of relying on friction pads, an EV can simply run its electric drive motor in reverse, turning it into a generator. The resistance of generating that electricity slows the massive weight of the car down and feeds that kinetic energy straight back into the battery. As battery technology scales and software becomes perfectly integrated with magnetic resistance, are we approaching a future where physical friction brakes, hydraulic fluids, and steel rotors become entirely obsolete? Will the cars of tomorrow stop using nothing but algorithms and the invisible pull of electromagnetism? Something to think about the next time you find yourself slamming on the brakes. Thank you for joining us as we unpacked the unseen forces that stop our world. Keep questioning, keep looking closer, and keep diving deep into the hidden mechanics of your world. See you next time.